Let's find the normalization coefficient for the ground state wave function of the quantum harmonic oscillator. In the previous video in the quantum mechanics playlist, I found that the ground state wave function in the position representation had the form of a Gaussian. The aim of this video is to normalize that wave function. And to perform the normalization procedure, I need to know the integral of a Gaussian from minus infinity to plus infinity. So that's the Gaussian integral. So that's the first thing that I need to find in this video. So I'm going to define a quantity, capital I. This is capital I over here. I'm going to define that as the integral from minus infinity to plus infinity of e to the minus x squared dx. So this is not the most general form of the Gaussian function, and I will actually generalize it after I find the value of this. So I'm going to use the substitution trick to generalize the result to the wave function that we want. But this is just e to the minus x squared. It's a simple Gaussian function. It looks like a bell curve when you plot it. So what we're doing is we're taking the integral from minus infinity to plus infinity. That's over the entire x-axis. That's the entire one-dimensional domain. This integral by itself is very difficult to solve. So I'm going to have to use a trick. What I'm going to do is I'm going to square this. I'm going to square the quantity capital I. So I'm going to put some brackets around this integral, and I'm going to square it. And this is a definite integral. We have the bounds of integration over here. So when we evaluate this integral, there's not going to be any x. The x is going to disappear, and we're just going to be left with a number. So what I'm doing here is I'm taking a number, and I'm squaring it. And when you square a number, that's the same as multiplying it by itself. So I'm going to write 2 copies of this integral. And then we're going to see that we can do a cool manipulation with these 2 integrals that I'm going to write. So we have the integral from minus infinity to plus infinity of e to the minus x squared dx. And then what I'm going to do is I'm going to change the label over here. I'm going to have another copy of the same integral, but I'm going to change the label from x to y. So I'm going to have e to the minus y squared dy. And that doesn't actually change the result because I'm just changing the label. This variable does not appear in the answer. So we're free to call it whatever we want. This can be any variable. But I've specifically chosen x and y. And the reason for this is because I'm going to go into 2 dimensions. I'm going to make this into a 2-dimensional integral. I want you to notice that this integral has no y dependence. And this integral has no x dependence. So this variable does not appear anywhere in this other integral. And that means we are allowed to move the integrals around. We're allowed to swap the order over here. So I'll write out what I mean. What I'm going to do is I'm going to turn this into a double integral. And inside that double integral, I'm going to combine these 2 functions. So I have e to the minus x squared and e to the minus y squared. And if I multiply those guys together, I can use exponential laws to combine those 2 guys together. And that's going to give me the sum of the exponents. And I can factor out a minus sign, and that's going to give me e to the minus x squared plus y squared. And we're integrating with respect to x and with respect to y. I've turned this into a double integral. And what are the bounds of integration? Well, both x and y are going from minus infinity to plus infinity. So you can think of this as integrating over the entire plane. So what does this look like if we graph it? If we graph it and we have the function as a function of x, that's just going to be a single variable function. And it's going to look like a bell curve. That's what the Gaussian function looks like. So this integral, when we evaluate it, actually tells us the area under the curve. It tells us all the area that is enclosed underneath the Gaussian curve. But what does this tell us? This goes into 2 dimensions. So we have an x and a y axis. That's our xy plane. It's a 2-dimensional plane. And from there, we can have an axis that tells us the value of the function. And the Gaussian function, if you have two inputs, x and y, it looks like a bump, a 2-dimensional bump. But it's actually 3-dimensional because we have another axis that tells us the value of the function. So we're taking a plane, and every point on the plane has a value of the function. And it looks like a bump. It's a hill. And what we're doing is we're finding all the volume underneath that hill. That is what this evaluates to. So you can think of this as the integral over R2. That's the 2-dimensional space over here, whereas this is just a one-dimensional space. But this is still not very easy to integrate. I don't know how to integrate all of this stuff over here. But what I can do is I can change the coordinate system and make it into a coordinate system that is easier to perform the integral in. And I know a coordinate system that can simplify this integral a lot, and that is the polar coordinate system. So I'm going to write this two-dimensional integral, this double integral, in polar coordinates. So I'll do that underneath here. So I'm going to have polar coordinates, and it's still going to be a double integral. Okay, so we still have these two integrals over here, but the bounds of integration are going to be different. And this function is also going to be different. What is x squared plus y squared when we go into polar coordinates? Well, if you remember the Pythagorean theorem, this is the same as the radial distance squared. So x squared plus y squared, that's the same as r squared. And we're using r, that is the radial distance in polar coordinates. So then we have minus r squared. What's going to happen to this dx and this dy? Well, dx and dy, they're actually going to turn into r d theta dr. Where did this r come from? Well, this r is actually the Jacobian. You have to introduce this r when you do a transformation, when you go from Cartesian coordinates to polar coordinates. In general, it's not going to be r. In general, it's going to be some function that depends on the coordinates. So this is a specific transformation that takes us from the Cartesian coordinate system to the polar coordinate system. And this is in 2 dimensions. If you're dealing in 3 dimensions and you're going to spherical coordinates or to cylindrical coordinates, you're going to have different factors that you have to introduce here. A physical way to think of this is as a little chunk of area, right? dx in one-dimensional calculus is a little infinitesimal chunk of x. It's a tiny nudge in x. What about dx dy? Well, that's a tiny little slice of area. So a tiny little slice of area has dx as one side and dy as the other side. You can think of it as a tiny little rectangular tile. And when we do the integral, it's almost like we're breaking up the entire 2-dimensional plane into a bunch of infinitesimal tiles. And those tiles have side length dx and dy. But when we go into polar coordinates, the tiles have this little area over here. This combination gives the area of these little tiles. And we have to introduce r because the area of the tiles actually gets larger when you move away from the origin. So that's why we have r d theta dr. So we've switched to theta and r as our variables. Theta is the angle going around. It's the polar angle. So this angle needs to go from 0 to 2 pi radians. So we're measuring this in radians. So I'm going to write the bounds of integration over here. We're going to have 0 to 2 pi. What about r, the radial distance? Well, if we take the angle to go all the way around, then we actually don't need negative values for the radial distance. We only need positive values and 0. So we start at 0. When r is equal to 0, we're at the origin. And then as we move away from the origin and go all the way to infinity, that takes care of all of the 2-dimensional plane. So we start at 0, and then we go to infinity. I could write plus infinity, but I'll just write infinity. There is no ambiguity. So x and y both go from minus infinity to plus infinity. That takes care of the entire 2-dimensional plane. But r and theta don't have to go from minus infinity to plus infinity. Theta only goes one full revolution. It goes from 0 to 2 pi radians, whereas r goes from 0 to infinity. It has to go from the origin out to infinity. If we included negative values for r, if we had minus infinity over here, we'd actually be doubling up. We'd be counting we'd be going around the circle and then we would count it again. So we would count the same chunks of the 2-dimensional plane twice. And that's not what we want. We only want to count it once. So what I've done over here is I've just transformed this integral from Cartesian to polar coordinates. And this is going to be easier to solve. I want you to notice that now we have no theta dependence in here. Everything depends on r. So we can turn this into a single variable integral. So this d theta, we can swap around. We can move this over here. And that's going to be the integral d theta from 0 to 2 pi. And that's just going to introduce a factor of 2 pi. So I can rewrite this as 2 pi times the integral from 0 to infinity of this function over here. We have r times e to the minus r squared. So we have r times e to the minus r squared. And this is with respect to r. We're integrating with respect to r. So this factor of 2 pi has just come from integrating with respect to theta. So we have d theta over here, and I can move this d theta over here, and I can take this integral from 0 to 2 pi, I can take that out, and I can factor it, and we can have the product of two integrals. That's exactly what we did over here in reverse. Over here we had two integrals by themselves, and then we moved them together, we smushed them into a single integral. Over here we're doing the reverse. We have an integral over here, and then we're taking it apart into the product of two integrals, and one of those integrals is just giving us a constant. So we have 2 pi, and 2 pi physically corresponds to rotating one full revolution. So this actually does have rotational symmetry. The Gaussian in 2 dimensions is rotationally symmetric. So you can just take the one-dimensional Gaussian, rotate it around, and that will trace out the two-dimensional Gaussian. So let's have a look at what we've actually done. We have turned this back into a one-dimensional integral. And now what I'm going to do is I'm going to evaluate this one-dimensional integral. I can rewrite this in a slightly more suggestive form. I can take this and write it as minus pi as the integral from 0 to infinity of minus 2r e to the minus r squared dr. Have a look at what I just did there. I've introduced two minus signs, and if I move this minus 2 back outside, that's going to give me 2 pi. So that's all I've done. I've just moved this 2 inside, and I've introduced two minus signs. But I've made this a lot more suggestive. Have a look at this function over here, minus 2r. That is the derivative of what sits up in the top. If you take minus r squared and you differentiate that with respect to r, you're going to have minus 2r. The derivative of a quadratic is going to give you a linear function in r. So what we can do is we can notice that this actually came from applying the chain rule. So we can find the antiderivative of what is inside over here. So that's going to give us minus pi, and I'll write the antiderivative. The antiderivative is just e to the minus r squared. And r is going to go from 0 to infinity. So those are our bounds of integration. So can you see if I take the derivative of this, I'm just going to get back this integrand. So the derivative of e to the minus r squared with respect to r is going to give this same Gaussian function multiplied by the derivative of this exponent. So the derivative of what's being exponentiated, and that is minus 2r. So that is just a little manipulation that you can also do via substitution. You can also solve this integral via substitution, but I think this is more suggestive. So now let's evaluate this function from r equals 0 to r equals infinity. So what are we going to get? We're going to get minus pi times what happens if we take the limit as r goes to infinity. So if r becomes a really, really big number, this exponent is going to become very, very negative. So we're going to have minus a really, really big number squared. And that's a very, very negative number. And if you know the graph of an exponential function, if we go all the way back to minus infinity, it's going to asymptote towards 0. So this is actually going to give us 0. So we're going to get 0 from evaluating the function at infinity. So what about r equals 0? So what happens if we substitute r equals 0 over here? Well, if we substitute r equals 0, that's e to the 0, and e to the 0 is 1. So that's 1. And here we have a minus pi times minus 1, so we get pi. The answer is pi. Isn't that miraculous? So the square of this is equal to pi. So what have we done? I'll do a very quick recap because there's some non-trivial steps involved over here. I've taken a one-dimensional integral of the Gaussian function over the entire x-axis. I've squared that integral, and that's given me two copies of the same integral. I wrote one of those copies with a different variable. I've labeled this as x and this is y. Then, because there is no dependence of, there's no x dependence over here and there's no y dependence over here, I'm free to rearrange the order of integration. And I can combine this into a single two-dimensional integral. It's a double integral over the entire xy plane, over the entire two-dimensional plane. And now what I can do is I can write this in a different coordinate system. I can transform from the Cartesian coordinate system in 2 dimensions to the polar coordinate system, which is in terms of the radial distance and the angle theta. So that also introduces a factor of r. And it is this factor of r, which comes from the Jacobian of the transformation from Cartesian to polar coordinates, that simplifies the integral. Because without this r, we would be unable to do this integration step over here. So that r is why I chose polar coordinates. Polar coordinates are very convenient because of this factor of r. So another important thing that I want to stress is that the reason we're allowed to swap these guys around actually comes from Fubini's theorem. And Fubini's theorem is a concept in maths that tells you when you're allowed to combine the integrals together and to move those integrands together and combine them into a single integrand or split them apart into two separate integrals. So you can sometimes factor multidimensional integrals into single variable integrals, and those are easier to solve. So the conclusion over here is that I squared is equal to pi. And so from that, we can conclude that I is equal to the square root of pi. So I is equal to the square root of pi. And from that, we can also conclude that, write this in different color, the integral from minus infinity to plus infinity of e to the minus, I'm going to write another name for the variable, I'm going to write it as z squared dz, that is equal to the square root of pi. So why is this a positive root? Well, the area under the curve is positive. The Gaussian function always has positive values, so the area is going to be positive. We're defining it to be positive. And we're going from minus infinity to plus infinity. So our sign convention means that this has to be the positive root. So I, this value of capital I, is the square root of pi. So we have the square root of pi over here. Now what I'm going to do is I'm going to do a little substitution. I'm going to do another substitution trick. I'm going to define z as being equal to, actually I'm going to take z squared. I'm going to define that as a times x squared. I'm going to generalize this to the case where this coefficient out the front is not equal to 1. So if I take the square root of both sides, that's actually going to give me dz. dz is going to be equal to the square root of a times dx. So if I square root both sides, it's going to get rid of these squares, and it's going to turn this a into the square root of a. And then if I differentiate both sides, dz is going to be equal to dx with this coefficient out the front. So now what I want to do is I want to substitute these values into this equation over here. And what's that going to give me? Well, I'll write it over here. That's going to give me the integral from minus infinity to plus infinity of e to the minus x, oh, actually I'll write ax squared because I want this coefficient over here, ax squared dx. That is going to be equal to the square root of pi over a. Now can you see where that has come from? If I substitute z squared equal to ax squared, that's going to give me this. I'm going to have minus a squared over here. And if I substitute dz, dz is equal to the square root of a times dx. So that's going to give me an extra factor of square root of a inside the integral. But a is just a constant. So I'm free to move that constant outside of the integral and then divide both sides of the equation by square root of a. And that's going to give me this expression over here. So I have this Gaussian integral, and that's equal to the square root of pi over a. And in general, this is true. For any coefficient over here, any coefficient you put here, then all you have to do is you have to divide the square root of pi. Underneath this square root, you have to put that coefficient. And that's exactly what we're going to do when we normalize this wave function. So now I'm going to do the normalization procedure. We want 1, the area of 1 under the curve, to be equal to the integral from minus infinity to plus infinity of the ground state wave function, which is labeled by psi sub 0. That's what we found in the previous video in the quantum mechanics playlist. So this needs to be equal to 1. That is the normalization coefficient. So what I can do is I can take this wave function, I can take out the coefficient. I can take out that normalization coefficient, which in the previous video I called capital A. So I want the capital value, so this A over here could be complex in general. I want this capital A, the absolute value squared, times the integral from minus infinity to plus infinity of this ground state wave function, of the Gaussian function. I want that to be equal to 1. So I'm going to write it over here. We have e to the minus m omega over h bar x squared dx. But have a look at this. There is a missing factor of 2. I've taken that factor of 2 out of the denominator. That's because I'm taking the square over here. And if I square this Gaussian, that's going to bring in an extra factor of 2 into the exponent. That's part of exponential laws. So that is where this missing 2 has come from. So in the normal wave function, I would have had 2 h bar over here. And that's what you saw in the previous video. But have a look at this integral. This has exactly the same form as this form over here. this coefficient A, is equal to m omega over h bar. So now I can do this substitution. I can just look at this form and substitute that over here. So the absolute value of this coefficient is going to be equal to, actually, this coefficient times the square root of, we're going to have to take the reciprocal of A. That's going to give pi h bar over m omega. And all of that is underneath the square root. So we have pi h bar over m omega. M omega over h bar, that is the value of A. And over here we have a square root, and over here we have squared, right? So what we're going to have to do is we need to ensure that this times this is equal to 1. So we can take the reciprocal of this, move that to the other side, and that's actually going to tell us what the absolute value of A is equal to. The absolute value of A is going to be the reciprocal of that, m omega over pi h bar, but it's not going to be the square root. We have to square root it again. That's going to be 1 over 4. That's the power over here. That's the exponent. And where's that 1 over 4 come from? Well, it's because we have a squared over here. A square root is the same as 1/2. That's the power of 1/2. And if we square root that again, that's going to give us 1/4. That's a half times a half in the exponent. So now we can write the ground state wave function in its normalized form. So I'll write that over here. Psi sub-0 of x is equal to m omega over pi h bar to the power of 4, to the power of a quarter, 1 over 4, times the Gaussian function. This Gaussian function has the form m omega over pi, actually 2 h bar. So we have 2 h bar over here, and x squared. So that is the Gaussian that we have over here. Over here we have a 2, and over here we have a pi. This m omega over 2 h bar is in the exponent, and a pi is over here in the normalization coefficient. So this is pi and this is 2. So can you see how when we squared this, we got rid of this 2? And that's why there is no 2 appearing in this exponent over here. We just have an h bar by itself. That 2 disappeared from the denominator. So we found this general result for the Gaussian integral, and we use that result to perform the normalization procedure on the ground state wave function of the quantum harmonic oscillator. One important thing I want you to notice is that this is the absolute value of A. This in general could be a complex number. It could have a phase. We could multiply this by e to the I times some angle. But that would just complicate things. We want a real coefficient over here. It doesn't matter if we multiply this by some unitary coefficient. If we have e to the I something, that's actually not going to change the physical significance of this wave function. Multiplying or adding a phase to a state doesn't actually change the physical interpretation. As long as you multiply by the same phase, as long as all the states get multiplied by the same phase, it doesn't have any physical significance. You're still having the same physical description of the problem. So this is the ground state wave function of the quantum harmonic oscillator in the position representation. It has a similar form in the momentum representation. And in the next video, what we're going to do is we're going to find the excited states of this wave function, of the harmonic oscillator. And it's going to be very interesting. We're going to see this normalization coefficient appearing again. So make sure you watch that video. You can find it in the quantum mechanics playlist over here.